Have we started? Yes. Okay. Welcome to the talk. We had some technical difficulties, so we had to kind of put together an ad hoc camera setup, but we have a mic now. It seems to be working okay. It's covered in chalk, so that's okay. Today we're talking about, starting to talk about surgery theory. This is sort of a follow-up to the H-cobordism talk, but in essence, it's kind of its own thing, even though, as we're going to see in 1 second, we're going to use the H-cobordism theorem as like an entry point into a lot of the ideas that we have to talk about today. So if we bring our attention over here to the far left, was the actual title of the talk. So this is a paper by John Milnor in 1961. It's called A Procedure for Killing Homotopy Groups of Differentiable Manifolds. The idea, the procedure, is something that we now call a surgery. And the idea was it's a geometric modification of a smooth manifold that produces a new smooth manifold. And the purpose of the paper was to try to study when can you, given some piece of algebraic data, like a homotopy class or a homology class, can we represent this thing by some smoothly embedded trivial neighborhood of a sphere, and then do the spherical modification to that to get a new manifold? If we do that, how does this algebraic invariant change? And in particular, the overall question we want to answer is, can we actually eliminate all of the topology of our smooth manifold, starting at the bottom and working our way up to the middle dimension, using the spherical modification procedure that I'm going to present in a minute? So I mentioned also there's another source by A.H. Wallace. Everyone always says John Milnor invented all of this stuff. A.H. Wallace came up with a lot of this stuff around the same time. I unfortunately didn't look into this manifold, or paper, so I don't know how big of an intersection there is. John Milnor says that he came up with much of the following material independently. So I don't know exactly how much, but at least the bits about doing the procedure, how does it affect homotopy groups, how can you tell when you can actually do a procedure to kill a particular class and stuff like that. So this is the title. So we're going to jump in. Okay, so I said surgery theory. This is supposed to be our first foray into surgery theory, the very basic introduction of where it comes from and what does it do. In a very broad question, what does surgery theory actually do? Probably the primary purpose is for manifold classification. We have these things called manifolds. You can have topological manifolds. You can have smooth manifolds, where you have a smooth atlas. All the transition functions are smooth functions. And you can have something intermediate between those two called a PL manifold, where you just ask that the transition functions be piecewise linear as functions from Rn to Rn. And so when you're studying surgery theory, there's kind of a ladder. You want to ask questions about, can you go from top to PL? And if you have a PL manifold, what's the obstruction from going to PL to smooth? So this is related to something called smoothing theory. We're not going to jump into that today, maybe never. Things like the Kirby-Ziebenman invariant come from smoothing theory. Can I write his name correctly, I think?
Is this also related to the canonical way of smoothing out corners in smooth manifolds with corners?
That's kind of like there's no deep theory that happens there. It's just you can do that. Yeah, so I'm going to talk about the surgery procedure. If you're not super duper careful, you get a manifold with corners, but there's kind of a standard way of smoothing out the thing. That's not quite the same. There's manifolds that you start with that are topological manifolds that you actually can't put a smooth structure on. And so smoothing theory kind of studies why does that happen? How can you tell just based on some of the algebraic invariants whether you can do it or not? So stuff like this is kind of the special space, one of the special spaces people like to think about. They call it top mod O. What does that really mean? Well, there's this kind of group. It's not really a group. It's the set of all self-homotopy equivalences of an n-sphere. It's a topological monoid because things aren't invertible on the nose, only up to homotopy, but it still has a classifying space. Inside of that, there's On plus 1. The orthogonal transformations of Rn plus 1 also acts on the n-sphere. Turns out if you have a topological manifold, it doesn't have a tangent bundle in the same way that a smooth manifold does. It has this topological micro bundle, which is still classified by a map to B top. And so smoothing theory ends up saying something like your topological manifold with its classifying map to B top admits a smooth structure if and only if this lifts to BO. And the number of smooth structures is given by the different homotopy classes of lifts. And by putting BPL in the middle, you can break your problem down into two pieces. Might as well put that in the middle there. So this is kind of the sophisticated perspective of all of this stuff. Though we're not actually going to do that sophisticated today. We're going to be working at the ground level, hands-on things. But this is kind of what's going on in the background. We're trying to think about questions like, do you admit a smooth structure? And if you do, how many smooth structures? So B top is like you have the monoid of homotopy equivalences of the n sphere back to itself. And you don't actually have to have a group to come up with a classifying space. Like a monoid, it turns out, is enough. And so you can do, well, there's a much more complicated than what I just said. You end up with a simplicial group is one way to do it. Milnor has a construction. He constructs this simplicial group. There's one group for every n. And you get a classifying space by taking a geometric realization of this simplicial group. It's a delicate. You can't just say, here's a group, here's its classifying space. There's something a little deeper going on there. I'm definitely going to get wrong if I just try to explain it off the top of my head. Like a lot of the stuff that I'm going to talk about today, I'm probably going to be wrong. So people at home, like and subscribe to the YouTube channel, put some comments, tell me where I'm wrong. Okay, so our goal for today, the next talk, the talk after that, we're hoping to understand specifically homotopy spheres. So out of all of the smooth manifolds in existence, we're considering specifically the ones which are homotopy equivalent to the boundary of the standard sphere. So we want to be able to count how many of these things there are up to diffeomorphism. This is the task for the next few talks, is to understand homotopy spheres. And there's, well, it's actually a group. So I'm going to just say maybe, I'll just define it like this. This isn't really the correct definition. But I'll define it like this. We take theta n as the set of diffeomorphism classes of homotopy groups. Homotopy spheres, rather, sorry. We seek to understand this thing. It's going to turn out this is a group. We'll see why maybe in a couple talks. We don't need to know that it's a group yet, but it turns out it is a group. This helps us really to grasp what this thing is, just knowing that it is a group. Okay, so with kind of the introductory stuff out of the way, I'm going to jump into sort of the technical bits that we use to study this stuff. First tool, this is something I outlined a proof of in my last talk. It's called the H-cobordism theorem. So if you fix your dimension to be at least 5, so now we're in the high dimensional regime, at least 5. If you take two manifolds which are smooth, closed, meaning compact and without boundary, so the boundary is empty, oriented, and simply connected manifolds, then, so if you have an H-cobordism between them, which recall an H-cobordism is a manifold of one dimension higher, say W, so that the inclusion maps from either of the ends into W are homotopy equivalences. I'm just going to write HE because I get very, very lazy. So if you have your smooth manifolds with these conditions are H-cobordant, then in fact they are diffeomorphic. So the condition of being H-cobordant is a relatively weaker thing to check. You just have to find this So instead of cooking up, these might be weird abstract manifolds, might be really hard to cook up an actual diffeomorphism between them. It might be easier to abstractly come up with an H-cobordism between them. To check, once you've come up with a cobordism, to check that it's an H cobordism, just evaluating some algebraic invariants to see what you get. Being simply connected actually means that to check this, you only have to do a calculation on homology. You actually have to check that this relative homology group is 0 to get a homotopy equivalence in this particular case, because everything is simply connected. So this is our big tool. How is this useful to us for this particular task? So I'm going to call this the fundamental lemma. This is what the entire surgery apparatus procedure is about. So if M is simply connected, dimension at least 5, then if M is the boundary of some W where W is contractible, then M is actually diffeomorphic to the standard sphere. So this is a check, right? This is way easier than coming up with a diffeomorphism. You just have to find some smooth manifold that M is the boundary of. If it's contractible, then you get a diffeomorphism, and it is the standard sphere. So I'm going to outline kind of how this proof works. I mentioned it at the very end of the last talk, but I'd like to draw attention to like the algebraic tools that we're going to use in order to do these things. Okay, so here's what we do first. So choose some embedding, some standard disk. Phi from the standard disk into the interior of W. So we wanted the disk to land away from the boundary. So let's map something into the interior of W. And then we're going to let W, I'm going to do like physicists do and put a slash through things. I'm going to set W slash is W minus the interior of this embedding. So here's kind of a picture. So here's my M. I don't know it's a sphere, so I'm going to draw it wobbly. And then here's my W. It's just some contractible manifold, not necessarily a disk, so I'm going to draw that wobbly as well. But then we have some actual embedded disk. So this is phi of D. I don't want to draw it too small. Viewers at home. So here's our actual standard embedded disk. And you remove the interior of this disk to make W bar. So now you can see that the boundary of W slash is equal to, well, on one hand, you have M. And then on the other hand, we want to choose our orientations so that the other boundary component is actually the standard sphere with the opposite orientation. So we can choose our phi to make this happen. Right, so if you don't get if you don't get this orientation, you can just replace phi with something that like reflects first to swap the orientation. So our W bar is, so this should be a union. So what this is saying is that W bar is a cobordism between M and the standard sphere. So what we need to do is check. Oh, oops, well, that's too bad. I hate breaking up proofs, but that's okay. So we want to check, in order to use the H cobordism theorem, let's check that this W slash is an H cobordism. Then we're done. And like I said, it's enough to do a homology calculation in this case. So first of all, notice, if you take your W bar, mod out by your spherical end, this is the end that we have control over, this is going to be homeomorphic to if you started with your W and just modded out the entire disk. So because we're like creating the singular point, you can't say anything about diffeomorphism anymore. But right, so all we're doing, the difference is you're taking the interior of this disk, crunching all that down to a point along with the boundary. That's the same as just not including the interior at all, because it all just goes down to the point anyway. So since this is like a nicely embedded contractible space, this quotient is actually just homeomorphic to W to begin with. So we can just pinch off our little standard sphere in our W bar, or W slash, and end up with W again. So when you do a homology calculation, we get this. So this is what we want to compute. If this is 0, this means we have an H-cobordism theorem, an H-cobordism, because our ends are simply connected, so it's enough to check relative homology. So we can do first something I'm going to talk about a bit later. You can go from homology to cohomology in a manifold with boundary using something called the Poincaré-Lefschetz duality. It's in my notes to talk about this later. I might talk about this right after the proof first, though, just so while it's fresh in our minds. So now that we have this and the sphere, so the relative homology group, since this is sitting inside of this manifold, is a nicely embedded submanifold. It has a colored neighborhood. The relative homology and cohomology is the same as just the reduced cohomology of the quotient. So this is a normal fact from algebraic topology. Nothing really complicated going on there. And then, like I said, this quotient itself is homeomorphic to W. So we get to just write this in right away. W is contractible. So we get 0. We're not quite finished. So all we've done is we've computed that the, oh, no, we are. Yeah, like I just said over there, we are. Okay, yeah. So the groups that we needed to be 0 are 0. Therefore, W bar is an H-cobordism. I actually didn't state the H-cobordism theorem completely correctly. What I meant to say is that the bordism itself is diffeomorphic to the cylinder. It's even stronger than just saying that the two endpoints are the same. It's the bordism, the wavy bordism that I drew here. It's actually a straight bordism. It's actually a cylinder. And it follows from this, as a slight corollary, the diffeomorphism here is relative to the M part. So when you take W to the cylinder on M, and you compare to what it's doing at the M part of W, it's actually the identity on the M part, which means that the N part goes to the other end of the cylinder on M, so meaning that M and N themselves are diffeomorphic. So that was a little mistake. It's actually slightly stronger, but the upshot here really is that M is diffeomorphic to the standard sphere. All right. So this is some of the algebraic tools going into this type of story. Yeah.
What if the like n is greater than equal to 5 assumption sort of like work? That's where the H-cobordism theorem.
Yeah. You have to be able to do the Whitney trick. So you have basically, yeah. There's something called the Whitney trick. It needs the dimension to be at least 5.
Okay.
That's the only reason.
That was for the fundamental lemma rather than for the H-cobordism.
Yeah. So this restriction in the fundamental lemma is because we have to use the H-cobordism theorem. That's exactly right. So this fundamental lemma isn't true in dimension 4. It's not true. Okay. So given this fundamental lemma, this suggests a strategy to us. So suppose we want to know if M is diffeomorphic to the standard sphere. And again, we're in high dimensions. Suppose we want to know this. If this is a big assumption, if M is the boundary of some manifold, so for some, can we modify W, leaving the boundary intact, until the resulting manifold, say W bar, well, not W bar, W prime, is contractible. So this is a potential strategy. If you have a manifold, you want to see if it's a sphere or not. And if you know it bounds some manifold, if you can like do things in a controlled way to that manifold to result in a new manifold that has the same boundary, but the new manifold is contractible, then we can apply our fundamental lemma and say, okay, M had to be the standard sphere. But that's a big if. It's not true that every manifold is the boundary of some other manifold. And even if it is, you can't necessarily succeed in doing these modifications. So what we want to try to address, so if we can't modify, if not, how can we tell? Right? It's usually really hard to prove that you can't do something in math. To show that you can do something, you just have to exhibit it. In order to show that you can't do something, you need to have some profound fundamental reason for why it can never work. So this is
What is H dot E dot?
H dot E dot?
In the bracket drawing.
Oh, I'm just saying homotopy equivalence.
Okay. And E dot. Oh, okay, that's just like a shorthand of this. Okay.
Yeah, one word each. Yeah. Yeah, I'm just going to get really lazy. I don't want to write all the word out the entire time. Okay. Thank you to the camera crew doing the hard work. Okay, so Kervaire and Milnor. So after this paper, Kervaire and Milnor worked together as a team to really, really crack this problem. So Kervaire and Milnor identified things that are now called surgery obstructions. And they use these surgery obstructions to study this space, the set theta n that I erased. And the rest of the talks will be about identifying and describing these, at least in some cases. Okay. Sure. Okay, are there questions yet about kind of the overall idea and what we're aiming to do? And maybe don't ask why we're doing it, but just, you know, is it clear what we are doing? And, yeah. Okay.
Why is W mod GN isomorphic to W?
It's because you just have like a contractible, yeah, how can I say this in a rigorous way? So it's kind of clear that it's homotopy equivalent, and that's all we actually need in order to prove this. So if I wanted to be a little more careful.
You don't have to be rigorous. A intuitive geometric shrinking with your hands proof is sufficient for you. So you just do that to the DN side of W.
Yeah. Kind of like here's your manifold, and then here's your disk. Here's your disk, and then you have another manifold where your disk is pinched down to a point. And so the idea is kind of like, okay, the natural map pinches us down. That's obviously not a homeomorphism. So what you have to do is kind of pick a little neighborhood around this point and like kind of dampen the pinching so that only the middle point goes to the center point, and then all of stuff you're pinching down goes to the rest of this. That's not really an argument. No, hold on. Yeah, how would you say this rigorously? Yeah, so the natural map makes it too small. Yeah, the idea is kind of, as long as the disk is embedded into the interior, you can make like a slightly bigger disk. And then that slightly bigger disk comes down to be a disk around your collapse point. And then I guess what you would want to do is take your slightly bigger disk here and just modify your map so that instead of this big disk mapping to this big disk, the disk that you collapse maps to this disk instead. I don't think that's a very good explanation, but
Doesn't the disk
that's one way of
match
doing
the
it.
point?
Yeah, but you want to modify your map.
But you said it's not a homeomorphism, but we don't care if it's a homeomorphism. We're just saying it's homotopy equivalent, right?
Yeah, so it's easy to see that it's homotopy equivalent because you just have to expand the point out again. But it turns out that you can construct a homeomorphism. The quotient map is not a homeomorphism, but it can be, you can construct a homeomorphism nevertheless between these two manifolds.
But for the proof, we don't use it, right?
No, you only need to use homotopy equivalence because of, going from here to here, you're just going from there to there. And you only need a homotopy equivalence to get an isomorphism on those groups.
Yes. For homotopy equivalence, you just use the tilde, not the equal, like a one-line tilde.
Yeah, this is my homotopy equivalence. It's bad notation. Maybe I'll do this for homotopy equivalence and a tilde for a cobordism. And then I'll label it with a H or a D, depending on if it's a H cobordism or what.
Well, you usually use the tilde for equivalence, right? When you want out those equivalence.
Yeah, the equivalence, this time I'm using a specific equivalence and I'm giving it a name. Tilde bar. Okay. Did I just do this?
You just wrote that.
I just wrote that. Okay. Okay, so now let's do the surgery procedure. So this is the actual modification procedure that you would try to use on a manifold to change its topology. And again, A.H. Wallace thought hard about this stuff, just like Milnor did, and he came up with a lot of the stuff that is about to happen independently. So let's take an M, smooth oriented. So just to define it, you don't need the M to be compact or anything like that. You just need to be smooth and oriented. Suppose we have say an oriented embedding. We're going to take phi. So we're going to start with a sphere of dimension k, and we're going to thicken it up to make a manifold that has the same dimension as our manifold M. And we're going to want to embed this into the interior of M. So we want to avoid messing up the boundary of M if M happens to have a boundary. So then what we do is we take this out. In particular, we want to take out, what am I saying? Yeah, we want to take it out. Yeah, I didn't do a good job of writing these notes. Out this image. And notice, so the boundary of this weird thing, well, boundaries work like this with manifolds. Yeah, so this is a little side. So since this is closed, boundary of Sn is empty, we're just going to get Sk cross Sn minus k minus 1. But this is the same as the boundary of dk plus 1 cross Sn minus k minus 1. So I can't go, oh no, it's the worst.
For the case, we're saying can we modify W such that it would contractible?
Yeah.
If not, there's a surgery obstruction with a good example of being able to remove it if we have a cobordism that's not an H cobordism between two elements of Sn that have topology, that has topology, so just a genus or some genera in between, and
Something like that.
yeah, something like that, exactly. And we can just like remove that obstruction. So we can turn W into a H cobordism, and the ends stay the same.
Something like this?
Yeah, and this is homotopy equivalent to or even homeomorphic to just the cylinder.
Yeah. So this is an example of what you can do to a manifold with boundary. So here I took an embedded sphere, and I pretend this is like thickened up to actually be an annulus. So this is S1 cross D1. And then I glued in a D2 cross S0. So here's a D2 cross S0, and that's the same as just having a cylinder. So for example, yes. But in this case, we didn't have a surgery obstruction because we could do a surgery. So there was no obstruction to doing the surgery. The obstructions are things like CP2. Here's my drawing of CP2. So we have the inclusion of the 2 skeleton in CP2. And you can't surger this away. And the reason is because you can't get a trivial normal bundle. So I'm going to say a bunch of stuff about this right away, but this is where we're going. So the idea is, right, like I said, in this example, in this drawing, I'll exaggerate this more. So we want to take this donut and turn it into like a horseshoe, right? So we can try just taking one of our homology generators for this donut that we kind of want to get rid of. And the way that we get rid of it with the surgery procedure that I haven't actually even written down yet. So we needed to embed the S1, but then thickened by a disk. So in this case, we can. We can embed S1 thickened by a disk. And once we have our S1 thickened by a disk, then we can take it out and glue in the complementary thing. In this case, we can embed our S2 into CP2 to represent the generator of the second homotopy group. But you cannot embed it with a trivial normal bundle. So you can't thicken it with the embedding with a disk. So there's no embedding of this guy. So there's no, so it doesn't extend to the thickened thing that we would need it to. So having that product is really saying that your embedded sphere has a trivial normal bundle. So I'm going to actually say things about that. You asked a question at the right time, but I am going to say something. Okay. So I haven't actually said what is the surgery procedure, right? I just drew some pictures. Okay, what am I doing? So we want to do like chi-m. This is the modified manifold. This is equal to m minus the interior of phi of sk cross dn minus k. So you take this manifold with the interior of your solid tube deleted, and then you glue in along the boundary. So the boundary is going to be an sk cross s n minus k minus 1, and then you glue in a complementary thing. Okay, so this is the picture. So here's, for example, a special case of this is called the connected sum. So if k is equal to 0, this is called the connected sum. So suppose our manifold had two components, and suppose we embed. So then we have what? S0 cross dn. Well, this is just two disks, right? So here's one of our disks. Here's another one of our disks. And so the whole idea, now we use colors. So there's one boundary component of this solid tube, and then the other boundary component is like this. So when you take out the red things and then glue in the blue thing, is what we're doing here. So that's what it looks like in the easiest possible case, where k is equal to 0. You can go look up pictures or try to draw pictures for higher dimensions, but it does obviously get really hard to conceptualize when things start to add up to numbers that are bigger than 4, which is what we're doing. We're in dimension 5 and up, so it's kind of hard to visualize. But this is the basic low dimensional visualization that you can think of. This is the simplest version of our surgery procedure. Yes?
Is the sphere of the, let's say I have some n-dimensional manifold called M that is closed, and I want to connect it with the sphere of the same dimension. The sphere, is it just the identity of your homotopy?
Yeah, you get the same. Yeah, you get a diffeomorphic manifold back. So if you take any manifold, yeah. So this is something that's covered in the literature, in Kaczynski in particular. So this is the notation for a connected sum. It's not a very explicit notation, but if the things you put on either side are themselves connected, then it is well defined. And so if you change your embedding up to isotopy, then the resulting manifold is going to be diffeomorphic. So the result that works here is that if you have a connected oriented manifold, then there's only one isotopy class of oriented embeddings of the disk. So there's only up to diffeomorphism one choice you can make. But the point is, if you take the connected sum of any closed manifold with a sphere, you always get a diffeomorphism back to the manifold you started with. What's interesting is that when this is an exotic sphere, then you get a homeomorphism to the manifold you started with. It might not be a diffeomorphism. So that's
always a homeomorphism.
You do always get a homeomorphism. If this manifold is homeomorphic to the standard sphere, then taking a connected sum with it does give you something homeomorphic to what you started with.
Can you define isotopy, please? Or is it if it's...
I can just say it in words. An isotopy is like a homotopy through smooth embeddings. There's also an ambient isotopy, which means you're applying an isotopy that starts at the identity map of the manifold, and that like your particular function is kind of being dragged along this ambient isotopy of the whole manifold. So this is actually like an ambient isotopy thing. That's something, yeah. I will not dive into that. I encourage you to go read some technical books on differential topology to learn more about that. Yeah.
So the surgery procedure is this creating this manifold here.
Yeah. So this is when k is equal to 0. That's what it looks like.
I mean like the chi.
Yeah.
That's your surgery.
Yeah. You delete the one thing and then you glue in the complementary thing.
Okay. And what you were saying about the CP2 is that if I do this on CP2, then I'm not getting rid of.
I'm saying that you can't do it to CP2.
Okay.
I'm saying that like when you look at this 2-sphere embedded into CP2, it doesn't have a trivial normal bundle. So this embedding of S2 into CP2, you can't extend that to S2 cross D2. And so that actually you're not even given the option of trying to do surgery on that. Yeah, good question. So as always, so this is related to handle attachments, obviously. Maybe not obviously, but it is.
Just make sure I understood. So the problem is like I can't even find this embedded here.
Exactly. Yeah. So this is going to be a big part of the story is we're going to start with an embedding and we're going to say, does it extend to this product? And we're going to have to find algebraic reasons why it does or doesn't. Yeah. So related to handle attachments. So here's the key thing. Like I said, with this little stuff down there, I'm going to write it like this. Not disjoint union. Not a disjoint union with the complementary thing. And their common intersection is the part that's just 2 spheres. So what we're actually doing, so a surgery on M, an n-dimensional manifold, corresponds to a handle attachment on, say, the cylinder. Or any manifold that has M as one of the boundary components, we can sort of stage the surgery on M by witnessing M as the boundary of something, and then just stick a handle onto the boundary. So here's a picture of what a handle attachment looks like. You start with your M cross I. Here is your product of disks. And so here's one of your sphere components. We'll do it in colors again. All right, so here's your one spherical, here's your sphere cross disk, and here's your chosen embedding. And then here's the rest, complementary part. And then so you do the handle attachment, and you get something that looks like this. Right, so as far as this upper boundary component is concerned, we've removed the red things and glued in the complementary blue things. But as far as like the bulk manifold with boundary is concerned, all we've done is taken the solid tube and stuck it on top. So these two are related. And so like we saw last time in terms of handle attachments, so here's one thing that's true. So M, should I say this here or write this here? Yeah. So M is oriented cobordant to N if and only if there is a sequence of surgeries, feed the cats, starting from M, ending up at N. And we call this relation chi equivalence because this is the name that we gave to our surgered manifold. So in fact, if you want to study oriented cobordism, it turns out that surgery is a powerful tool for helping you do that. Okay, so that's a setup. So this is our procedure. So we're going to start to think about all of these questions I've been alluding to. How can you tell when the surgery is actually possible? And what happens to your manifold if you're able to actually do the surgery?
Can I ask a question?
Yes.
So for the CP2 case,
I love that
is
case.
the problem about the existence of phi like is it the orientation, or is it just like straight up, even if you remove the orientation? I don't have a good intuition about what this is going. So
yeah, a lot of this picture is sort of designed for oriented manifolds. Some of the things kind of don't really make sense if it's not oriented. The problem in that case, which is what we're going to see in a bit, is that if you compute the intersection number of that thing with itself, you get something that's non-zero. So if you have a submanifold and it has a trivial normal bundle, you can just perturb it away from itself. So the self-intersection would be 0. So if you don't have a trivial self-intersection, you already know that there's no trivial, well, at least for like middle dimensional manifolds, you can tell that way. But yeah, we're going to see on the next page somewhere, we're going to see really soon how you can tell. Are there any other questions related to that? Pretty good? Okay. So here's kind of the general question. Given a piece of like algebraic topology data, for example, you might have a homotopy class. You might have a homology class. So can we represent this data using a phi from sk cross dn minus k embedding into M? And so the idea is like if you restrict phi to the spherical part, right, and call this maybe phi tilde or something, phi bar, phi 0, I think they call it. Right, if you just restrict to the sphere, then you're going to represent a homotopy class, or with the Hurewicz morphism, also a homology class. And so the idea is that when can we represent these things, not just with an embedding, but also with an embedding that has extended to the solid cylinder.
That's how you pronounce Hurewicz.
Hurewicz?
That's how you pronounce it?
That's how I pronounce it.
Oh, it's like Hurewicz.
Hurewicz? I'm not the same.
Yeah, I was shocked.
I don't speak whatever language he's from. So, that's how I've always heard it with all my teachers. They say Hurewicz. So yeah, question. Given this data, can we represent it with such an embedding? And if so, what is the effect? I never remember how to, I don't think I've been spelling it wrong the entire time. I think that's how you spell surgery. Okay. And I don't use that word. Okay. Okay. Is it about CP2? Because I'm going to erase it.
About this definition. So what a sequence of surgeries this? You mean like if I start from M, apply this, I get the next one. Apply this again, I get the next one, and so on. Is that what you mean?
Yeah. So I can write it a little more overt. So there exists, say, M1 up to Mn, so that M equals M1, N is Mn, and then for all n greater than or equal to 1, some other thing, I. So we have some phi I going from a sphere, k sub I cross d n minus k sub I. N is obviously a bad thing to use. It'll have to be j, I guess. And then such that, right, so that M I plus 1 is chi M phi I. Mi phi I. Yes. So this is what you said. Yeah, you have a sequence of manifolds. For each manifold, you've chosen some embedding. You did a surgery on that manifold, you get the next manifold. So the first manifold is M, and the one that you end up with is N. That's what chi equivalence means. And it's the same as just saying that they're orientedly cobordant, and then the relation is through Morse theory. Given a cobordism, you choose a Morse function. Each of these Morse points is the same as adding a handle. Okay, we're done with the CP2. Okay. Holy moly. Okay. Glad I didn't prepare too much. Okay, so here's when the Milnor part starts. Okay, suppose. Let's look at a particular dimension. So let's take an alpha, a homotopy class of degree k, inner manifold n, and let's suppose that it's quote unquote below the middle dimension. So the k, the degree, can't be as much as half of n. So by Whitney embedding, we can represent alpha with an actual embedded map. So we have an F0 going from the sphere Sk into M, an actual embedding of a sphere, smooth embedding. So this is just a dimensional consideration. The Whitney embedding theorem just guarantees that we can do this. So the question is, do we get extension to this disk, the solid thing? So Milnor, from the main paper, this is lemma 3. So this F, the one that I wrote down here, in terms of this alpha, extends to our solid thing if and only if the pullback of the tangent bundle of M is trivial over our sphere. Okay, so M has its tangent bundle. It's a bundle. We have some continuous map that happens to be a smooth embedding. We can pull back the tangent bundle, get a bundle over the sphere, ask if it's trivial or not. It turns out if it is trivial, then we can make this extension. So here's a proof sketch. There's not really going to be any complete proofs. Here's a sketch. So the first one, which is not really immediate. So F star Tm is trivial if and only if, like I keep saying, that the normal bundle so I'm going to write mu sub F0. I'm supposed to be writing zeros everywhere. If and only if the normal bundle of this embedded submanifold is trivial. So in one direction, it's kind of easy. So the sphere is stably parallelizable. So if you add even a single trivial direction to its tangent bundle, then you trivialize it. So if the normal bundle is trivial, the pullback of the whole tangent bundle of M is going to be isomorphic to the tangent bundle of the sphere plus the normal bundle, right? So this is going to be the tangent bundle of the sphere plus the normal bundle. So if the normal bundle is trivial, then their sum, since this is stably parallelizable, their sum is going to be trivial. So that direction's pretty straightforward. The other direction's a little trickier. It involves some obstruction theory and some geometric argument. So it's not completely obvious why this is true. It is. Once you have that this is trivial, so if the normal bundle is trivial, then we can choose a tubular neighborhood. So you can always choose a tubular neighborhood that represents your normal bundle. If your normal bundle is trivial, then the tubular neighborhood is trivial as well. So it's going to be f of sk. This is inside of this open submanifold U, which is sitting inside of M, where U is just diffeomorphic in a fiber-preserving way with this product. And that's messy. Draw more clearly. Try not to draw so low on the board. So this is my proof sketch. So the first step is to translate it in terms of normal bundles. Then once you have it translated in terms of normal bundles, you can just appeal to the tubular neighborhood theorem and find your nice extension inside that tubular neighborhood. So that's okay. We have some geometry happening there. But this is a Milnor paper, so we have to be doing some algebra at some point as well. So this actually corresponds to an algebraic criterion. So consider the classifying map of this tangent bundle of your manifold. So we have M, tangent bundle of M, is classified by a map to BSON, because everything's oriented. And so if we have some function f from the sphere to M, then what does it mean for the pullback to be trivial? Well, this happens if and only if the homotopy class of f is in the kernel of this homomorphism. So pi km, this is where our homotopy class of f lives, and you just take pi k of the classifying map into pi k BSON. So this is algebraic topology way of saying exactly the same result. All we do is we're considering the tangent bundle as a continuous function to this classifying space. And then we're saying that for any continuous function, the pullback, well, that's just what you get by precomposing, right, with this f. And so the tangent bundle being trivial means that this homotopy class from the K-sphere into BSON is null homotopic. That's just saying that this homotopy class lives in this kernel. Yes, excellent. Okay, so this is our algebraic criteria. So what is the effect of doing surgery? So I have the lemma, but I didn't actually understand the proof fully, partly because I kind of accepted to give this talk at the last minute, and partly because I spent too much time thinking about the wrong things. So here's the result. So if dim m is at least 2k plus 2, so like one bigger, yeah, so k has to be not at the middle dimension, but then also like one less than that. And so we have some embedding setting up our surgery for us, prepping the surgery. And then we let M prime be the surgered manifold. So then what we get, so pi I of M prime is isomorphic to pi I of M in degrees less than the degree where we're doing the surgery. And in the degree where we're doing the surgery, what you get is a quotient of the manifold you started with by some group G, where our homotopy class F lives in G. So it's not necessarily the subgroup generated by F, but it is some group that contains F, so that when we do the surgery, in this particular degree, K, it looks like we're taking a quotient by that big group. So in effect, we've actually annihilated this homotopy class. It's important that we've left all of the lower homotopy groups alone, but then what can happen is that in higher homotopy groups, maybe everything changes. But if we want to start at the bottom and work our way up, this provides like an avenue for doing that. So if the lower homotopy groups are the way that we want them to be already, we know that by doing homotopy in higher degrees, we don't affect those lower groups. And we are specifically targeting homotopy classes that we want to get rid of. We can sort of target and get rid of those classes, assuming that they satisfy the criteria for actually being able to do surgery on them. And note, like, this is still like well below the middle dimension. All of this stuff is happening. So again, unfortunately, I didn't even find like an intuitive hand-wavy argument for how this argument works. Unfortunately, I guess I did manage my time well enough. Okay. So that is what is the effect. Okay. So as a consequence, one thing that we can say from all of this work that we've just seen, if M is compact, so compact means that all of the homotopy groups are going to be finitely generated in this case, because it's a CW complex, oriented, smooth, could have a boundary, and we're actually going to only say that n is at least, n is at least 2. Good thing I didn't want any of those chucks. Then M is chi equivalent to some manifold M prime where all of these maps to BSOK, BSON are injective for what? K1 less than or equal to K less than or equal to N minus 2 over 1. Right? Because the criteria for being able to do the surgery is that a thing lives in a kernel. So you can actually just attack the kernel and eliminate all of the homotopy classes in these kernels until you result in a manifold so that all of these maps are just injective. There's no way you can do surgery on the manifold at all anymore. And so in particular, if this map classifying the tangent space happened to be null homotopic to begin with, then you can just get rid of all homotopy classes because, everything is in the kernel. Yeah, so I notice, so this is kind of the extreme case. So if Tm is trivial, then we can get rid of all homotopy. Less than these degrees. So that's the idea. So sometimes you can and sometimes you can't. So if you want to start with your sphere and hope that it bounds a manifold and then try to do surgery on that manifold in order to, make that manifold contractible, we're going to need to make sure that like all of these maps are actually 0 for K small enough.
What is that map exactly that goes from the homotopy classes of M to like the classifying space?
What does it do exactly? I mean, like you just start with this map, and then what you would do is, just start precomposing with functions from a sphere.
Oh.
And so, like, given a function from F to M, F from the sphere to M, you turn it into a function from the sphere to BSON just by putting the Tm in the middle. Yeah, so this is just the induced map on homotopy groups that you would see like a second after you define homotopy groups. Yeah.
Is there an intuition as to why you only kill n over 2 minus 1?
It has to do with like the embedding problem. Like you have to be able to actually get an embedding. And so far, like if you go up by 1 degree, things get a lot more interesting. You can kill some things, but you have to do a lot of work, thinky work, to figure out how. So far, like we've only done like basic differential topology considerations with like the Whitney embedding theorem and stuff. So this just guarantees that you get an embedding. Yeah. So, like I said, if the tangent bundle of your manifold is trivial, then you could potentially get rid of all homotopy groups. An issue with this is maybe I've said something wrong already. So if you do surgery on a parallelizable manifold, parallelizable means that the tangent bundle is trivial. The result might not be parallelizable anymore. So I guess my this corollary is not actually maybe true, as it is true, but you have to know something else. Be parallelizable. Because you can't just continue the process indefinitely, because if you make something that's not parallelizable anymore, you're out of luck. So here's an example. If you start with S1 cross S3, these are both Lie groups, so their tangent bundles are trivial. If you do surgery to get rid of pi 1, you get an S4, which is not parallelizable anymore. But it is almost parallelizable. if you add a single trivial direction to its tangent bundle, you do get something that is parallel, you do get a trivial bundle. And so there's a slightly weakening of parallelizability called stably parallelizable. And an equivalent, this is what Milnor uses to save himself a lot of ink. This is called a pi manifold. Pi for parallelizable, stably. M is a parallelizable manifold if the tangent bundle of M, direct sum with a trivial rank 1 bundle, is isomorphic to a trivial rank n plus 1 bundle. So it's not necessarily a trivial tangent bundle, but if you stabilize it once, then it becomes trivial. So the canonical example for this is the sphere, the n sphere, because it's sitting inside of n plus 1 dimensional space. It has a trivial normal bundle. If you add that normal bundle to the tangent bundle, you just get the tangent bundle of ambient space, Rn plus 1, which is trivial. So the upshot here is that surgery does preserve the property of being stably parallelizable. Parallelizability. So parallelizable things are not quite the right thing to think about if you want to just do iterative surgery. Pi manifolds are. And so, in fact, what I should have done is save this statement for over here and written it like this instead. This was my mistake. I think it is still true. If you start with a parallelizable manifold, do surgery to it, I think you get a pi manifold back. So it would have worked, but you need the caveat that this is what's actually happening. These are the preferred class of manifolds. Yeah, so this is theorem 2. It's actually not easy to see. So I encourage you, if you really want to know how that works, go look it up. And this is, again, surgery below the middle dimension. This is what is stated by theorem 2. So this is the class of manifolds you'd like to work with to try to make this thing work. And then the corollary, what I just said, is this. Okay, so things are going okay. Okay, so that's kind of the easy case. We've dealt with like the easy case. If we start with a pi manifold, compact, oriented, smooth pi manifold, we can eliminate all of the homotopy groups up to this middle dimension, which should have like a floor on it because n's not necessarily an even number. Okay, are there questions about this stuff before I just jump forward? Okay. Let's see. A non-trivial example of a stably parallelized manifold. Let me think. Is there a good one that's not just a sphere? I mean, I think any. I don't want to say like genus G surfaces. Oh yeah, I think a genus G surface is going to be stably parallelizable. Anything that you can embed into a Euclidean space with a trivial normal bundle is going to be stably parallelizable. So I think a genus G surface works. So the thing about genus G surfaces is they have Euler characteristics, but the Euler number dies when you add a trivial thing to it. And so like genus G surfaces also have these Chern classes, but like these things aren't robust under adding real vector bundles. They're stable after adding complex vector bundles, but if you just add like real stuff to it, you can kind of break all of that structure. Yeah, sorry I don't have a better example. it's kind of easier to find parallelizable. They like occur most often in the wild, like groups and things. If you have a manifold with boundary, this is something I'm going to end up talking about in a later talk. Manifolds with boundary, the notions of stably parallelizable and parallelizable are the same. The idea is like you can take the obstruction to parallelizability, push it away to the boundary, and then just kind of like push it off. Very roughly, that's what happens. Okay, so what about the middle dimension? This is where surgery theory actually starts to happen. So far, we've just seen some like kind of low-level, relatively elementary differential topology. But now the algebraic stuff has to start kicking in a lot more seriously than just some kernel of some homomorphism. So let's go. And so I'm going to write it like this. So odd manifolds have two middle dimensions. I'm not going to talk about odd manifolds today. Let's just talk about even manifolds. What? I don't know what I'm talking about here. So let's say n equals 2k. And we want to do surgery in degree k. So can't use Whitney for free. But what you can do is you can get an immersion. So we can take a map, vk to m2k, any map. Transversality plus some other stuff. So we can modify, let's call it f, we can modify f to be an immersion, which means that the derivative of f is injective at every point. And then transversality is saying that we have isolated double points. So then what we're going to do, well, not me, Whitney did this, something that's kind of similar to the Whitney trick used in the H-cobordism theorem. Whitney has this like double point removal procedure. To actually eliminate these things and create an embedding. This is also something that I should have taken the time to look up and make sure that I understood the subtleties of it. Because I'm kind of just using it as a black box to eliminate these double points and actually end up with an injective immersion, I guess. Okay, and so next thing. This is, in particular, you can do this if n is bigger than 4. So this is one of these things where you're going to have some immersed disk that's bounding some loop that's connecting two double points, and you want it to make an embedded disk. So to do that, your ambient dimension has to be at least 5. So same constraint that we had in the H-cobordism theorem. So this kind of assembles into this lemma 6, which says that if M is simply connected, I think I needed M to be simply connected here. That would make more sense. So let's say M simply connected up here. Pretty sure to do the double point elimination procedure, you're going to need M to be simply connected. Simply. This is where you get your Whitney disks from, and your dimension constraint lets you embed them. So if M is simply connected, and dimension of M is even and bigger than 4, then any homotopy class in the middle dimension is represented by an embedding. So that's half the battle. We got an embedding. Remember that the ingredient that we needed to prep for surgery is that you need an embedding with this trivial normal bundle, or equivalently that the pullback of the tangent bundle is trivial over the sphere. So problem. Trivial normal bundle? So this is where things get really good. Okay, so our dimension is 2k. This breaks into two cases, depending on if k is even or not. So if your manifold's dimension is divisible by 4, versus if your manifold's dimension is congruent to 2 mod 4. So we're going to spend the rest of the time discussing when the manifold's dimension is divisible by 4, because this is sort of the easier version, and it introduces a lot of the tools that are used in the other case. So for us, let's just do the easy one. So k odd. So we'll focus on k even. Sure.
It's about the first board. So I know with this embedding, I don't know the general form. I just know the lot embed like n dimensional manifold into R2n. Or I guess the easy case is R2n plus 1, but you can further push down to R2n. And I assume like what you said before with embedding is like a similar thing for general manifold. But you're saying here the 2k case.
Yeah.
Like if I have a k, I cannot put it into 2k. Like what you did for Rn, like for Mn and to R2n doesn't work for.
I'm thinking that it does work. You just have to assume your ambient manifold is simply connected.
I see.
So when you're mapping into R2n, like it's contractible, you can just fill in any disk you want. Here, to do the double point elimination thing, you're going to need to sort of connect the 2 points with a pair of loops, and you want to get rid of them. So you're going to, put in a disk, and then you have to embed that disk. So just to get a disk bounding that loop, you're going to need simple connectivity. So I think, yeah, good question. Again, I wish I had spent more time understanding the subtleties of that. But you're right, yeah. So the 2n plus 1 case is the easier one, and then you have to do more work for the 2n case. But that work goes through if your manifold is simply connected, the ambient manifold, not just R2n. I hope chat will let me know, I guess, if I'm not completely correct there. Okay. What is he doing up there? I think we have enough time to go through the following proof sketch. Okay, this is probably the last thing that I do today. This is the genesis of this whole thing. So let's let M be a pi manifold. Dimension n equals 2k, and let's just say k is equal to 2p. All right, so it's divisible by 4 case. So now let's let beta, we're going to do things slightly weirder now. We're going to choose an element in homology rather than homotopy, and suppose it's represented by an embedded sphere. Embedding. And I'm going to do F0 from SK embedded into M. So, a priori, this is a homotopy class. But then you use Hurevich homomorphism to push it forward to a homology class. So suppose we have a homology class. Suppose that it is represented by embedding already. So then we're going to find that the normal bundle of this embedding is trivial if and only if the so-called homology intersection pairing of beta is 0. And so equivalently, what does this mean? So take G transverse copy of F and compute the transverse intersection number. Yeah. So this is what I was saying earlier about the CP whatever. If you have this half-dimensional submanifold, this normal bundle is going to be trivial if and only if its self-intersection is trivial.
And by transfer copy, you just mean like perturb them so you get some intersection.
Yeah. It's in the same homotopy class. Okay. So now mysterious things happen. Let me see. All right, I'll just plow forward because there's not so much time. So suppose we take mu in this homotopy group. Actually, I'm just going to do it the normal way. Yeah. So then, a connection of lemmas that I didn't discuss too much, lemma 3 and 4, which are based on obstruction theory, which I've never talked about in these seminars, so I can't even begin to say stuff. If we take our normal bundle, add a trivial thingy, then you get a trivial bundle. So the normal bundle is stably trivial by some lemmas and some obstruction theory. So now consider the stabilization map. So this is something that exists on the level of groups. SOK goes to SOK plus 1. You just add a 1 in the bottom corner or in the top right corner, depending on your preference. And then we get a fibration sequence. So this embeds SOK as a subgroup, and you can take the homogeneous quotient group or space. It's quotient space. Now the quotient space, SOK plus 1, is acting on SK. If you fix the first standard basis vector, the stabilizer subgroup is just everything orthogonal, preserving the orthogonal complement of that. That's a copy of SOK. So the homogeneous space, the quotient of these guys, is just an SK. And then by some stuff that I mentioned in my bundles talk, you can de-loop this to the right with the classifying spaces. So we can use this fiber sequence to get a long exact sequence of homotopy groups. I'm blocking the camera. So how do I want it to go? So let's say pi n plus 1 BSOK plus 1, boundary map down to pi n sk, pi n BSOK, pi n BSOK plus 1, etc. And so here's our stabilization map sitting in between those two groups. So this statement up here, that stabilizing once makes it trivial, means that if we take our normal bundle here, where the degrees is equal to k, stabilize once, we get 0. So by exactness, it comes from back here. So in particular, so i.e., mu is in the kernel of this map. Pi, this is not a good board. Yeah, okay. Not a good board. Again, I'll have a continuous proof someday. Okay. So in particular, unfortunately, we're over here now. So mu, the normal bundle, is in the kernel of the map pi k BSO k to BK blah blah blah, which by exactness is equal to the image of pi k sk to pi k BSOK. This is Z. And the claim is that this thing sends 1, draw your 1s better, to the tangent bundle of Sk. And my source for this is Steenrod, topology of fiber bundles. I think that there's nothing like extremely clever that he does there. Instead of talking in terms of classifying spaces, he just talks in terms of clutching functions. So instead of pi k BSOK, it would be pi k minus 1 of SOK. And he just really explicitly studies the boundary map of that long exact sequence, takes the identity function for a sphere, sees concretely what the boundary map does to it, finds out that you get the clutching function for the tangent bundle. So there's sort of, it's not some deep esoteric thing, but you have to actually sit down and do the work to see why the identity function here goes to this clutching function there. So I'll actually emphasize that the generator, the preferred generator of this group, is just the identity function of the K-sphere. Okay, so that's our black box. Meaning that, by exactness, so if V is in the image, so that V is equal to M times the tangent bundle, I'll write it like this, TSK, no. I'll call this tau. So by exactness, mu, which is in the image of this map is generated by the tangent bundle of the sphere. So nu has to be some multiple of the tangent bundle, where m is an integer, some integer. Okay, so we can compute which number this is. Using the Euler number, the Euler class. Okay, right. How much can I really say about this in the time allotted? So the Euler class is an obstruction class. It obstructs, it's the primary obstruction to finding a non-zero section for a vector bundle. It also has the property that if you have a closed oriented manifold, then the Euler class is equal to the Euler characteristic of the manifold. So those are the two relevant things. I'm just going to have to write some things down and stop dawdling. Okay, so nu is oriented, so has an Euler class. In the same cohomological degree as the rank of the bundle. And this is equal to k by sending a cohomology class to its evaluation on the fundamental class. So if you choose an orientation of the K-sphere, this gives you an isomorphism between these two groups. So this Euler class goes to, after you evaluate it on Sk, to something called an Euler number. So it's no longer a cohomology class. We've got an actual, honest to goodness, integer out of it. And so the claim, so here's one claim. It's not such a hard claim to make. Right, so for the rest of this argument to go through, it's important to know the following. So if you take oriented, B. So this group parametrizes the oriented K-plane bundles over the K-sphere. To each of those, you get an Euler class living in this group. And the claim is that this is a group homomorphism. So where the group structure on the left-hand side isn't direct sum, it's given by the sort of called folding map. So there's kind of like this pinch map going from the K-sphere to the wedge of two K-spheres. And you can just wedge together two functions defined like this into our space BSOK. So we can add two functions together by pinching first and then applying each function on each separate half because everything's pointed. So the vector bundle that you get is essentially, you consider a vector bundle over the sphere, consider another vector bundle over the sphere, and you have some chosen trivialization over this base point where the spheres are wedged together, and you kind of just expand out that base point. You have the one vector bundle over this half, the other vector bundle over the other half, and then there's sort of just a trivialized bundle over the middle. This is what the sum looks like for vector bundles on the left-hand side, and you'll just have to trust me that this translates to the cohomological sum on the right-hand side. So I will not provide more details than that, unfortunately. But the important part is that we get a homomorphism between these two groups. And therefore, our Euler number, so on one hand, the Euler characteristic, so the Euler number of the tangent bundle of the sphere, like I said, that's just the Euler characteristic of the two-sphere, sorry, of the two n-dimensional sphere, because k is even, right? So this sphere has a cell decomposition with one 0 cell and one k cell. If k is odd, the k cell gets a minus sign and you get 0. If k is even, the k cell gets a plus sign and you get 2. And so since the Euler number of the generator of this image is 2, and it's a homomorphism, then the image is free. So therefore, yeah, how do I want to say this? How did I write it down? Yeah, so therefore, if we call this map delta, just to be consistent with our notes, therefore the image of delta is a free abelian group of one generator generated by tau. And so if we take the Euler number of mu, our normal bundle, which you said our normal bundle is some multiple times the tangent bundle, this is going to be m times the Euler number of that tangent bundle, which is going to be 2m. So we can compute. So this m that we got is just exactly, well, we didn't actually compute it. Well, yeah, it's just half the normal bundle. Sorry, really tripping up my words now. We can compute this m just by knowing that the Euler number is a homomorphism. We can compute this m by just taking half of the Euler number of our normal bundle, which is interesting to notice that all of these normal bundles, they all have an even Euler number. So there are no Euler odd dimensional blah, blah, blah. There are no Euler numbers that are odd. Okay, so just in the very last minutes, I can wrap up this argument. I wish I had done this argument better because this was the one that was like most interesting to me. But I kind of just did a bad job putting it together. So here's a geometric interpretation of Euler number. So if n smooth oriented, the zero section embeds n into a manifold that's twice the dimension. I can say this differently. Given a smooth oriented manifold and V, a rank n bundle over n, smooth bundle. So this could be the tangent bundle of n, but it's actually more general. You still have a zero section that embeds your manifold n into a manifold of twice the dimension. and we can calculate the transverse intersection. Yeah.
You're using n for the rank of your bundle and also n for your dimension of big N.
Same number.
And now you have a 2n on the lower b to it.
Yeah, I'm abusing notation. Yeah, this is not a great notation.
Okay, so that's the rank and they want the dimension?
Yeah.
Okay.
I'll say it like this. I'll say rank n separately so that all of the subscripts only refer to the dimension as a smooth manifold. Yeah, so exactly, you choose a smooth manifold, you choose a bundle over it that's oriented, I should say oriented, whose rank is the same as the dimension of your bundle, so that the zero section is an embedding of a manifold into a manifold that is exactly twice as many dimensions. Then you can calculate the transverse intersection, because making a transverse means you have these isolated zeros. They have signs because everything's oriented. Add up all those signs, and you get a number. Fact. This number is equal to the Euler number of the bundle. So this is not obvious to see. So unfortunately, I can't say a lot about it. So in particular, you end up getting that if V was the tangent bundle of N, then the Euler number is equal to the Euler characteristic. So I should have said this first because I've already used it over there to compute the Euler number of the tangent bundle of the sphere. But that's too bad. Okay, so I already deleted the statement of the theorem, so I'll just finish right here. Okay. So now, so we've got our SK embedded into our normal bundle, nu F0, which by a tubular neighborhood theorem is sitting isomorphic to some open submanifold of M. So we have this embedded submanifold sitting inside of this normal bundle. So perturbing the zero section, what did I say here? Of nu F0 just means computing the self-intersection of Sn in M. That's just what that is, right? You just have your normal dimension directions in M. You're just bumping your sphere in your ambient manifold, computing the self-intersection. And this is how we defined our beta dot beta. And by the previous thing, I guess by this is equal to the Euler number of nu. And so we get that, why is this true? Yeah, so what is the point that I'm trying to conclude? I'm so close. I just have to say the words and we can leave. So we wanted to show that the normal bundle was trivial by showing that this is 0. Yeah, so therefore nu F0 is trivial if and only if the Euler number is 0, because we have this parametrization of these normal bundles in terms of multiples of the tangent bundle, where the multiple that you get is measured by the Euler number. And this is if and only if, by this argument here, because they're the same thing, the homology intersection is 0. Yeah, it's a bit of a complicated argument, but all of this was just to figure out by way of the Euler number as our key algebraic topological tool, that if we have this embedded submanifold, you want to know if you can get a normal bundle that's trivial, you can do this if and only if you can find that the manifold self-intersection is 0. So this is something that depends on the normal bundle. This is something that doesn't depend on the normal bundle. That's the point. So this is something you can compute without there being a normal bundle at all. And so if this thing is not 0, then you know you can't find a trivial normal bundle anywhere, because any normal bundle that you find is going to give you this Euler number. Okay, that's where we're going to end today. This is the first step in a series of steps about how to algebraically understand the reasons why we can't do surgery in the middle dimension. So finding out these trivial normal bundles is a good first step. So the next question is, can we find, sorry about using this board, a basis of the homology group, which are represented by embeddings with trivial normal bundle. And so, like, if you can, then you can do surgery on them to see what happens. But you can't necessarily do that. And we figured out how you can tell at the level of homology just by doing homology calculations. And next time we're going to see that these are actually cohomology calculations, whether or not you can actually find a basis that you have these embeddings with trivial normal bundles. And you're going to find that the obstruction is called the signature. So if you don't manage to make it to the next talk, I'll at least leave it with this takeaway. There's a very important invariant called the signature, and it's going to drive the entire rest of the next two talks that I'm going to talk about. This is what you do in the 4-dimensional case. The 4k plus 2 case, there's something that's a bit different called the Kervaire invariant. Surprise. I'm not sure if we're going to get to talk about that as much, so we're just going to focus on the signature from here on out. And that's all I'm going to say today. Thank you. Okay. Yeah. Sorry about that last proof. Thanks. Questions? Yes, please.
For the F plus G,
Yeah.
it goes from Sn Sk to
Well, I guess.
So it's doing Sk mod Sk minus 1,
Yeah.
and so that's going to be isomorphic to a wedge of 2 Sk minus 1s, right?
No.
No, sorry, Sks.
Yeah.
And then F, what is F? Wedge G is going to be defined on, the F is going to be defined on one of them and G on the other one.
Yeah, because these are both pointed maps. So you just basically choose your favorite homeomorphism between like this pinched top half and Sk and the pinched bottom half with Sk, and then you're applying F to the top half and G to the bottom half. So because the wedge is the coproduct in the category of pointed spaces.
The wedge is why the coproduct, not the product?
So a coproduct is defined by the way that you construct maps coming out of it. So a coproduct, the universal property is that, how do you say this right? So if you have a function defined on each piece coming out of it, then there's a unique map defined on the whole thing that restricts to each of the maps on each piece. Product goes the other way. A map to the product is determined by its coordinate functions, but a map out of a coproduct is determined on each of its pieces.
And so F plus G is the entire map from Sk to B, that's okay.
Yeah, this is how you would always define the plus map on homotopy groups. So if k is equal to 1, you can go and check that this actually agrees with your concatenation product on the fundamental group. Yeah.
Would it be just the free?
Yeah, it would just be like do one and then do the other. Yeah. Yeah. Okay. Other questions? Yeah. This map. Oh, the kernel of that. Yeah, so those are going to be all bundles whose Euler number is 0. Is there a good way of describing that? Maybe a million years ago, I would give you a better answer. It's been a while since I thought about it. Yeah, but yeah, this is exactly going to be those bundles that admit non-zero sections. because the Euler number obstructs you from getting a non-zero section. So if your Euler number is 0, this is going to give you all of those bundles that actually admit a non-zero section. So it's going to be the trivial bundle for one thing. I think in certain dimensions, this might be an injective map, but it's not always. So when k is equal to 4, for example, this is not injective. I don't remember. It's been too long. I'm sorry. Do you have another question? Is that what you wanted to?
So like there's the isomorphism there. Sorry, the isomorphism is that the consequence of that quotient in your program?
Which one? This one here? Oh, that's the tubular neighborhood theorem. So this is saying if you have an embedded manifold into like a manifold of higher dimension, then like there's an open neighborhood around that embedded manifold that is actually like diffeomorphic to like the normal bundle of that manifold in a fiber preserving way. So like this is like I could write this more clearly. This is sort of classical differential topology. Oops. So this theorem lets you like realize the total space of your normal bundle as an actual submanifold of your ambient manifold. So it doesn't really have anything to do with like the Euler numbers and stuff like that per se.
Question.
Yeah.
This intersection, self-intersection number. I know you have this result because that's a homology thing, right?
Yeah.
So I know you have this other result in cohomology. I think it's like one of the Lefschetz theorems. Like you have a vector field, you can count it like by the isolated zeros or something like that.
Poincare-Hopf theorem.
No, yeah.
Yeah.
Is that like the dual of this? Or?
Yeah. I mean that's basically what this is.
Yeah, that's what it looked like. So I was like, but I know this isn't homology, so it seemed like kind of dual. I wasn't sure.
Yeah. Yeah, so in the next time, so I mentioned Poincare-Lefschetz earlier, and then I said I was going to talk more about it, and I'm glad I didn't because I ran out of time. But like next time, we're going to talk about using Poincare-Lefschetz duality to relate this homology intersection pairing with like cohomology pairing. You actually take like the Poincare dual, so like if you have two homology classes, say A in H, K, M, and B in H, N minus K, M, then like the homology pairing, this is equal to taking like the Poincare dual of alpha cup with the Poincare dual of beta and then evaluating it on the fundamental class of M. So being able to take this weird transverse intersection product and express it just in terms of like the natural ring product in cohomology, this lets us do like quite a bit computationally. Where like over here you would have to do a lot of like fiddling around stuff. This is like we have some formal rules about how these things work in cohomology, and you can just do like formal calculations. Yeah.
I was gonna ask why it's called self-intersection, but that makes a lot of sense.
That makes sense.
Because like with the cohomology.
Okay, yeah, because what we're going to end up getting into, this is called the intersection form. Yeah. I mean, the reason it's called the intersection form is because it has this intersection interpretation. Yeah. It's just by phrasing it in terms of cohomology, the arguments kind of go a lot more cleanly, and you don't have to get your hands dirty with analysis quite as often. But that comes with the overhead of like Poincare-Lefschetz duality, and like I wave my hands at it and say it's true, but I can't give you a proof. So, yeah. Great. So we don't have time to show how to compute the volume of a tetrahedron and an octahedron today. I thought I would end early and I didn't at all. Okay. No more questions? Okay, thank you. Thanks.
Is there a way to see